This video explains the background and the objectives of the SOSPO research project. The SOSPO project addresses crucial challenges related to the ambitious goals set for the integration of renewable energy sources into electric power systems in the coming years and decades. In Denmark, these goals stipulate that by the year 2020, 50% of the electricity consumption should be supplied from renewable energy sources, and by the year 2035, all supply of electricity and heat should be based on renewable energy sources. Fulfilling these goals will result in a fluctuating power production that is dependent on the prevailing weather conditions. Such fluctuations impose major challenges for a stable and secure system operation. To quickly explain the concepts of system stability and security, it is useful to use such a conceptual figure as shown on this slide. The figure conveniently represents the region of all possible operating points for a given power system. This region can principally be separated into two subregions, since an operating point can either be classified as an unstable point or a stable point, as indicated here by the yellow region. When operating power systems, it is desired to operate within a subregion of the stable area, which represents operating points with a more robust stability. When operating within this area, the system operation is said to be secure, and the operators can be sure that the system will survive, for example, any single normal contingency that might occur. The reason why it will become a challenge to ensure a secure operation of the future fluctuating power system is related to how a secure system operation has been ensured in the conventional power system. The existing approaches to ensure stable and secure operation rely on time-consuming offline computations to determine secure system conditions. Such offline approaches have worked well for the conventional power system, where the power production is based on non-fluctuating energy sources. On the other hand, when the power production becomes based on non-controllable fluctuating energy sources, there will be a need for new methods that can in real time determine the level of stability and security of the system. Furthermore, when critical conditions have been identified, there is a need for methods that can determine which corrective control actions can be taken to avoid system instability and re-establish a secure system operations. Such methods will become essential to avoid system instability and large-scale system blackouts in the future power systems. This challenge is addressed in the SOSPO project, where the overall objective is to answer how to ensure a stable and secure operation of the future sustainable power system where the operating point is heavily fluctuating. This picture demonstrates how this challenge of ensuring secure system operation is approached in the SOSPO project. The left-hand side of the picture shows a future sustainable power system where a large share of the power production is based on renewable energy sources, a part of the consumption is controllable, and it's assumed that a set of synchronous PMU measurements that provides full observability of the system will be available in real time. The right-hand side of the figure shows various modules that are envisioned as parts of an integrated operational solution that ensures secure system operation in real time. Each module corresponds to a major research activity in the SOSPO project. The individual modules reflect the work package structure of the project. The operational tool is envisioned to work in the following way. Synchronous PMU snapshots will be received in real time from the future sustainable power system. The first thing to do before the data can be used is to make sure that the data set represents an actual operating condition. This will be done by methods that in real time validate the received measurement snapshot and replace faulty data with realistic estimates as needed. The output from this module will be a validated measurement snapshot, which will serve as input to a range of methods for assessment of system stability and security in real time. The assessment module returns situational awareness information when the stability and security margins of the current operating point have been determined. The situational awareness information serves as input into two modules that determine appropriate countermeasures against stability and security problems. The objective of the wide area presumption control is to resolve security problems by exploiting controllable loads and distributed production for that purpose. This module determines new presumption patterns that would re-establish secure system operation. The second control block determines effective emergency control actions to avoid emergent system instability and potential large-scale blackouts. The situational awareness information, together with the outputs from the control module, serves as input to a supervision and a visualization module. This module presents the state of the system to the operator in a crisp and informative way and makes sure to apply countermeasures when necessary. In the SOSPO project, we wish to demonstrate our research results in a realistic environment. For that purpose, a software demonstrator will be developed where all of the developed methods will be implemented into a single operational solution. For the testing and demonstration purposes, equipment from the state-of-the-art laboratory, PowerLab DK, will be exploited. This includes a real-time digital simulator that is used to represent a future power system, and a powerful IBM Blade Center that is used for software implementation. You can find more information about the SOSPO project and videos for the individual work packages on the project's homepage, sospo.dk. Thank you for your attention.